Today we will find out how to design 2-bit ALU, and for that what is the entity. So that entity we can realize on a black box. This is 2-bit ALU because we have a constraint on a board. We don't have that kind of number of LEDs and the switches, and that's why we have scaled down. Instead of 4-bit, it's a 2-bit. So here we will need 2-bit wide, two inputs, that is A, which is A 1 down to 0, and that is being 2-bit. Another is B, which is again 2-bit wide, and to select to get the output, I have again 2-bit output, which is nothing but I had defined here, it is as a Z. And when my addition is there, definitely I may find 2-bit may generate one carry, or may, when I am actually trying to subtract A minus B, that time a borrow may get generated. That's why I am defining another output which is single bit, and only in that case when that carry or a borrow is generated, that time only this will be asserted as a 1. Otherwise it is not utilized, and that time we will put it as a tri-state. There is again to select that is called as a total number of 2 arithmetic operations and 6 logical operations. We need a mode, and that is the mode which is nothing but the 3-bit wide, and that mode will have things like 000, 001, and here this will be utilized for addition, and this talks about A plus B, whereas 0 plus 1 it is A minus B, and rest of the mode, that is 00, 10, 011, 100, 101, 110 and 111. All these will be for logical operations, and this logical operation may have ANDing, NAND, then it's a XOR, OR, and blah blah kind of thing. I will just come to find out like exactly whatever this typical ALU structure is being designed. Same we will try to find out here. The ALU entity is being defined where the port A and B, which is 1 down to 0, which is a 2-bit wide. Z is the output, which is again that is called as a 2-bit wide, which is 1 down to 0. Carry borrow, that will asserted only when my addition is needing carry, addition is yielding carry, or maybe the subtraction is yielding borrow. That time only this is actually activated. Mode, this is 3-bit wide because I need to have 8 different operations. You will find out in a actual architecture we have written one typical variable inside the process. So definitely one need to find out why this variable is needed. Instead of variable, if someone is defining same as a signal, then what will be the impact? Definitely one need to learn, and we will definitely find out that time it will take one extra delay to generate carry and borrow operation, so that one can be verified. Here you can find out if a mode is first, that is the operation is addition, that is 000, that time we are actually concatenating 0 with the A, because my temp which is being defined as a 2 down to 0, which is actually needing 3 bits, but whereas my A and B, these are only 2-bit. So definitely to make A and B as a 3-bit wide, I had concatenated 0 concatenated A, same 0 concatenated B. So that will actually be now 3-bit wide, and that addition will be performed and it will be given to the temp. And if this addition is yielding like A is 11 and B is 10, definitely you will find out this typical addition will generate a carry. At that time only my temp of 3rd bit, temp of 2, that bit will be having value 1. Otherwise I don't have that value, and that's why I am using only temp of 1 down to 0 to store my actual addition result in a Z. And if my temp of 2-bit, if it is 1, behalf of that addition where carry is generated, that time only I am actually asserting C underscore B, that is nothing but carry. Here in this case I will treat this is carry is generated, that is 1, else it is not, and that is 0. Same we have repeated for the subtraction, though only this symbol we have actually changed here as the subtraction sign. Same thing, if it is my operation is 01 minus, that is called as a 10, where my MSB of A is 0 and MSB of B is 1, that definitely I will find out it will demand a borrow. In that case only carry underscore B, here you can treat this as a borrow is generated, and a rest subtraction you will definitely find out just behalf of temp of 1 down to 0, which is directly pushed to the Z. Further, we have other modes, which is nothing but the mode 010, which is for AND, simply A and B it is done. Similarly NAND, XOR, XNOR, OR, and the further operation, these are all logical operations we have carried out, and for that we have made each time, that is that typical logical keyword and NAND, XOR, XNOR, or these are being utilized. There is again ALU pass operation. That ALU pass, most of the processors they may need that your A bit, whatever data is there, that should be passed on the output side. So there 111, that mode is activated, and that's why Z is directly passed on a A. Further, if nothing is there, we have taken the last as a else clause. All other clauses are the else if clause. So in that we are asserting Z as a high impedance and another C underscore B, that is again high impedance. If this clause is not written, definitely it will again demand some more hardware. That to avoid that, we need to have the last by default clause where our output we need to assign neither 0 nor 1. Similarly, in each mode we have defined that C underscore B, that is again high impedance, and that is because unless and otherwise this is we have not defined, you may find again it will demand more hardware. Now let's find out. Already it is being checked syntaxed, place and root and other things are being done. We will find out through the programming, and once this program is run, the bit file is being loaded, and after loading that bit file you will find out the operation which is actually being performed on a kit. Here we have selected the switch, first switch, that is called as a switch number 7 and a switch number 6, that is for A of 2, A of 1 and A of 0, and this another switch that is called as a switch number 5 and switch number 4, this is being selected for the B operation, that B is nothing but B of 1 and a B of 0. These are my input which is actually shown over here, that is A 2-bit wide and a B 2-bit wide. Afterward we have the operation which is nothing but the mode, and that mode is actually being selected from the switch that is called as a switch 2, switch 1 and switch 0. So same thing you can find out in the netlist. So that is actually the UCF, and that UCF it is actually showing clearly my C underscore B, that is the output, and it is configured to the P7. Similarly Z, those are my output, those are configured to my LEDs, those are Z of 1 and Z of 0. Similarly A and B, just now I had actually talked about that those are the switches SW7, SW6 and then switch 5 and switch 4. Modes are actually being configured for the switches. You can see switch 2, switch 1 and a switch 0, and this way we have actually will try to verify the operations. We have to find out the actual addition and subtraction and the logical operations on LED 1 and LED 0, and in case of if the borrow or carry is generated, that will be shown on the LED 2. Now I'll just push the data from this side. Initially we'll put all my modes as a 0 0 0, and that time I'm actually trying to do the addition, like I'm actually making 1 and B is again 1 0. 1 0 plus 1 0, definitely it will demand the borrow need to be generated. If I make this as a 0 1, so this is nothing but A is 0 1, B is 1 0. So it will actually, the result is 1 1. Similarly, if I'm actually trying to find out, that is the mode is now 0 0 1. So that time, if mode is 0 0 1 and I'm actually trying to say my A is 0 0 and I'm actually demanding 0 0 minus 1 0, so that time my borrow is generated as well as my result of subtraction is there, which is nothing but 1 0. Similarly, if I'm trying to push, that is 1 0 and this is 0 1 and 1 0, so that again you can find out it is 1 1 and the borrow is 1. If I'm going for the next operation, that is nothing but AND operation, you can find out for AND operation it is 0 1 0 and 0 1 0 it is now being selected, and here in this case the ANDing of that is called as A is 0 1 and B is 0 1. So you can find out it is AND. Further, if I'm actually trying to make this both 1, so both ones you can actually find out over here. Similarly, further if I'm actually trying to push same way the further operations, that is the NAND operation, so which is nothing but this is 1 1. So here 0 0 0 0, so that's why it is 1 1. If I'm actually trying to make this 1, this is 1, so this you can find out this operation is 1 0. Similarly, one can verify the other operations also in a same fashion. If I want to pass the ALU the ALU pass operation is actually trying to ask you to push your mode and triple 1, and by that time my A, whatever I will actually put, that will actually passed on the output side. Now I had passed on the ALU so A bit, that is 0 1, so that 0 1 is passed. If it is 1 1, then 1 1 is passed. So that's it. Thank you.